So we're going to begin chapter 6 in the Sullivan book, and this is the area between curves. So what does it mean to actually find the area between curves? So we're talking about some sort of graph, and what is the area between two graphs that you draw a picture here. I can pick the right color. So let's think that we're talking about our xy plane. And I want to maybe find the area between the graph of y, or f of x equals 5, and then y, or f of x equals 1. So you want to find the area between these curves, but only between x equals 2 and x equals 6. So I want to know, what is this area? Well, that's just actually a rectangle, so we can figure this out. Really, it's a square. I mean, that's just going to be the base times the height. So we'll figure out what is this measurement. So if I'm going from y equals 1 to y equals 4, that measurement is 4. And then this measurement, so going from 2 to 6, that's also 4. So my area is 16. But that's not the only way that we can do this problem. We can also represent this in terms of an integral. So an integral represents area under a curve. So along the integral, you want to think of slices. So if I did top minus bottom here, if I took just a slice, so I'm going to put this in a different color. I'll put this in red. If I take a slice out of this rectangle, so think of it like an infinitely thin slice. That looks like a rectangle. So if I take that out, it looks like this little tiny rectangle. If we can figure out the area of this rectangle, then I could just add up all the rectangles, and that'll give me my total area. So the area of a rectangle is base times height. We already know that. What's the height of this little tiny rectangle? Well, it was this bottom line and then this top line. So if I do the top minus the bottom, that's 4. All right. Then what's the width of this tiny rectangle? Well, since it's infinitely tiny, we'll call it delta x. So it's just a little bit of a change in x. So then to find the total area, so I'll call this integral, a is the total area, we're going to add up the area of all of those rectangles. So 4 delta x is my tiny all my rectangles, and this becomes a dx in the integral, so 4 times dx. And then you got to decide, what are the bounds? So moving from left to right, what's the smallest x value? That's 2. And what's my largest x value? Well, that would be 6. So the integral that we want to find is the integral from 2 to 6 of 4 dx. So let's just do that real quick. The antiderivative of 4 would be 4x, and we're evaluating this from 2 to 6. So I'll do 4 times 6 minus 4 times 2, which is what? 24 minus 8, which is 16. So there's my answer to that first one. Now let's do a little bit of a harder problem here. Let's say that I want to find the area. So we're going to find the area between f of x, which is x squared plus 1, g of x, which is just x equals -1, and x equals 2. So the first thing that I'm going to do is I think we should graph all of this. So off to the side here, I'm going to graph this. So starting with x squared plus 1. So that first graph of f of x is just a parabola that's been shifted up 1. So let's draw that here. There's f of x. Good. Next we have g of x, which is just x. So that's just a line going through the origin. So there's my g of x. Then x equals -1. So x equals -1. I'll put it in a dotted line form. And x equals 2. Definitely not to scale. But here's the area that we're looking at. Shade this in. All right, so what we want to do is we want to take a slice out of this area, figure out the area of that tiny slice, and then draw an integral. So imagine that we took a tiny slice, and I'm going to draw it in blue. So take this tiny slice out of that area. We already know that the width of this slice is delta x, because that's being measured on the x-axis. But now we need to figure out what is the height of that rectangle. Well, the height's going to be the top minus the bottom. So it's going to be f of x minus g of x, and we have equations for that. So x squared plus 1 minus x. So that's my tiny rectangle, and that's what we're going to integrate. So you can almost think of the integral sign as adding up. So I'm going to be integrating x squared plus 1 minus x. Now I got to figure out the bounds. So bounds go from left to right when we're in terms of x. So what's my lower bound? Well, that's down here at x equals -1. That's where I start adding up rectangles. If you move left to right, so if I start here and move to the right, where do I stop adding up rectangles? Well, I stop at x equals 2. And let's not forget that delta x, because the area of the tiny rectangle was the height times the base. Now we'll evaluate this. So the antiderivative of x squared was 1/3 x cubed. Antiderivative of 1 is x. Antiderivative of negative x is minus 1/2 x squared, and we're evaluating this from -1 to 2. So I would plug in my 2 and get 1/3 times 2 squared. That should be a 3 right there. Should be 2 cubed. Plus 2 minus 1/2 times 2 squared, and then minus what I get when I plug in -1. So that'll give me 1/3 times -1 cubed plus -1 minus 1/2 -1 squared. Just plugging this into a calculator, I got 8/3 minus a -11/6, so 9/2 is my final answer. Really what we're thinking here though is that you want to do top minus bottom, but then where do you start adding up rectangles, where do you stop adding up rectangles? So I want to do 2 more of these. Let's find the area between equals the square root of x, y equals x minus 2, and the y-axis. So just like we did last time, I want to draw this. Figure out what does my area look like. If you need to use your graphing calculator, that's fine. Just draw this and figure out what our area is. So there's my xy plane. Square root of x starts at the origin, kind of has this concave shape. So there's square root of x. Next I have y equals x minus 2. So that looks like this. And then the y-axis. Now there's kind of two, the y-axis over here. There's kind of 2 little areas, this top one and this bottom one. That doesn't matter. We're looking for all of this area. So there's our area. Let me switch to different colors so we can figure out a slice. So we want to know what's that area. I'm going to start by taking a little slice from this area. And it's really important to notice that the top and the bottom stay the same throughout the entire area. I know that this is going to be delta x, so the width of that tiny slice. And then the height is going to be the function that was on top, which is the square root of x, minus the function that was on the bottom. Now the function that's on the bottom is x minus 2, and we're going to be real careful because you got to subtract off that entire function. So make sure and put it in parentheses. So it's time to build our integral. It's going to be the area of the tiny rectangle. So that area was square root of x minus x plus 2. I'm just distributing that negative. And then delta x. But we got to figure out, where do I start adding up rectangles and where do I stop? So if I'm kind of moving from the left to the right, I would start adding up rectangles right there, which is where x equals 0. And then I would stop adding up rectangles right here. So the question is, what x value is that? Well, it's where square root of x equals x minus 2. You could solve this in your calculator. It's x equals 4. So there's our integral. Going from 0 to 4, square root of x minus x plus 2. So let's do some antiderivatives. Keep in mind that square root of x is really x to the 1/2. So the antiderivative is 2/3 x to the 3/2. Antiderivative of x would be minus 1/2 x squared, and antiderivative of 2 is 2x. We're going to evaluate this from 0 to 4. So plug in 4. We get 2/3 times 4 to the 3/2 minus 1/2 times 4 squared plus 2 times 4. And if I go and plug in 0, I'm actually just going to get 0, so that's nice. And I got 16/3. All right. I want to do another one. I actually lied, I want to do 2 more. So the next one I want to do is the same problem. We're going to look at it a different way. So square root of x, y equals x minus 2, and the y-axis. Same picture, nothing's changed, exactly the same problem. So I have the square root of x, y equals square root of x here. I have x minus 2. Goes like this. And let's just change this. I do want to change this a little bit. Instead of the y-axis, let's change this to the x-axis. So the area between square root of x, y equals x minus 2 on the x-axis. Now I'm looking at this region here. Okay. The issue is, and this is why I changed it to be the x-axis instead of the y, is if you want to slice this vertically. So let's say I start taking vertical slices. Like, that's fine. You have the square root of x on the top and then the x-axis on the bottom. But then as you move from left to right, see how the functions change? So in this first little rectangle, it was the square root of x on the top and the x-axis on the bottom. But in the second rectangle I drew, it would be the square root of x on top and then the x minus 2 on the bottom, which means you would need to find 2 integrals to find the total area, which is fine. Nothing wrong with doing that. You could do it. But if you notice, the area, or the functions on the left and the right stay the same, regardless of where I am in the area. So let me draw that in red and let me show you what I'm talking about. If I look horizontally, do you see how that x minus 2 is always on the right and the square root of x is always on the left? That means that we should probably slice this horizontally and not vertically, because I can do it in one integral. So let's take the generic slice, and I'll draw it down here. Keep in mind, I'm drawing it like kind of wide, but really it's just infinitely tiny. Now, this area is delta y, right? And the reason is because I've sliced it horizontally, not vertically. Those slices kind of hit the y-axis if you think about extending them. Those purple ones hit the x-axis, so that would be delta x. As far as how wide is this, I'm going to do right minus left. So my rightmost function was x minus 2, and my leftmost function was the square root of x. Here's the issue. I'm not going to be able to mix up x's and y's. So we can't use this. What I instead want to do is solve both of these for x. So this would really be x is y plus 2. All I did was add 2 to both sides. And this function is x is y squared. So I squared both functions. Right, you can't have x's and y's. We need just x's or just y's. So instead of x minus 2, that function was actually y plus 2. And instead of the square root of x, that function was y squared. We're just putting everything in terms of y. Now it's time for my integral. So the area of that tiny slice was y plus 2 minus y squared dy. In terms of the bounds, well, instead of going from left to right like we did with x's, we're talking about y's. So if I kind of move up the graph, where do I start adding up rectangles? So if I start moving up here, I start adding them up right here, and that's where y is equal to 0. Keep going up. Where do I stop adding up rectangles? Well, I want to stop at whatever y value that was. And we did before, we know that this x is 4, which means that this y is 2. So there's our integral. Do the antiderivative, so it would be 1/2 y squared plus 2y minus 1/3 y cubed from 0 to 2. You want to plug in 2, plug in 0, and subtract. I'll kind of spare you those details, but please do those on your own. And I got 10/3 for mine.